I'm Cole, and today I'm going to help you answer this nice little physics question that we have here. So let's begin by just reading straight through the problem. So we're going to use this simulation. We're going to select a couple settings. We're going to use the idea that Earth's kinetic energy is equal to 1/2 of the gravitational potential energy between it and the sun to predict the sun's mass. Okay, we're going to state the hypothesis. We're going to use the hypothesis, and we're going to state whether it's supported or rejected. Okay, piece of cake. So the first thing that I want to start with is notice this sentence right here. That's a wonderful sentence for us, right? That's just a word problem. So we can put that straight into the form of an equation. So let's read literally left to right through the sentence right there. Use the idea that Earth's kinetic energy is equal to 1/2 of the gravitational energy. Okay, so one thing that we know about the Earth's kinetic energy is that we actually have two components, right? So we have the component that's orbiting the sun. So that's going to be 1/2 m, where m is the mass of the Earth, v squared, where v is the tangential velocity. But we also have the rotational component, right? The Earth is spinning, it's rotating. So for that, we have 1/2 I omega squared, where I is the moment of inertia and omega is the angular velocity. So let's write those two down. 1/2 I omega squared. And that's going to be equal to something. Before we move on, let's just simplify right away. What is I? So I, we can approximate the Earth as a sphere, right? Really, it's an ellipsoid, but we can approximate it as a sphere. And for a solid sphere, the moment of inertia is 2/5 mr squared. Okay, and that's going to be equal to 1/2 of the gravitational potential energy. So we know that gravitational potential energy is negative g big M little m over r, where r is the orbital distance, right? Same with this r here. So something interesting that we can note here is that really this negative sign is used as a direction, right? It's used to tell us that it's an attractive force as opposed to a repulsive force. So since we don't really care about that here, we're just going to drop it. We don't need it. So we're going to say G big M little m over r. Okay. So one thing that we can notice here that's quite nice for us is these 1/2 factors cancel, and these m's also cancel. So this simplifies down to v squared plus 2 omega squared r squared over 5 is equal to g big M, which is really the mass of the sun. I'm going to put that little circle and a dot there to represent the sun, over r, the orbital distance. So from here, really, let's just solve for m. So mass of the sun is going to be equal to, I'm skipping a couple steps here, hopefully you can follow, is going to be equal to r over g times v squared plus 2 omega squared r squared over 5. Okay, so let's look at what we actually know here. So we know g, and that's it, right? That's kind of all we know. But we do know that this r is the same r as this one. So we need r, we need v, and we need omega. Okay, well, what is omega? Omega here was representing the angular velocity of the Earth as it rotates, right, about its own axis. So we know that if omega is equal to the angular distance divided by time, the angular distance is 1 rotation, 2 pi radians. Well, how long does it take to spin? 24 hours, right? 1 day. So when you're plugging it in, just make sure you simplify that down to your SI unit so everything cancels out and you're good to go. There's omega. Okay, so another thing that we can notice that's quite nice for us right over here, we have an expression for V, right? So now this is going to become R over G times 2 pi R over T squared plus 2 omega squared R squared over 5. Okay, so what this really represents is this 2 pi is the circumference of a circle, right? So what do we know the circumference of a circle of? The orbit of the Earth around the sun, and we can actually get that from our simulation. Let me demonstrate by sharing my screen here. So if we go over to this, I'll hide this. We can choose our settings that we need. First scenario, path, measuring tape. We click play. Well, we have our radius, and we have our time. How long does it take for the Earth to orbit the sun? 365 days, right? So now you have your radius, your orbital distance, your time, you have G, you have omega. So plug everything in, make sure your units are in SI units, and you should be good to go. So let's look back at the problem. State the hypothesis you're testing. Our hypothesis is that this equation will give us the answer, right? Question 2, use the hypothesis to determine the mass of the sun. Well, to answer that, you just plug it in, right? And you get a value. Okay, and please state if the hypothesis can be supported or rejected and why. So for that, I would just compare the value that you calculate to the value of the known mass of the sun, which is 1.989 times 10 to the 30 kilograms. Thanks for listening.